Data centers are the backbone of modern AI infrastructure, yet a persistent inefficiency hides in plain sight. Production inference servers run their GPUs at maximum frequency by default, regardless of whether the workload actually demands it. During off-peak windows, bursty lulls, and low traffic periods, the GPU sits underloaded, but still consuming peak power. The energy is wasted, the hardware ages faster, and the operational cost compounds silently at scale. This decision support system guides operators from pre-deployment configuration through runtime monitoring and training and in inference. No changes to the training process or to inference server are required. The artifact employs Halo Hybrid Adaptive Latency Optimized Controller that detects latency slack at inference in real time, reduces GPU frequency to save energy, and recovers immediately when the SLO boundary approaches. Together with the operator-facing dashboard, the artifact presents an end-to-end solution. The system is accessed through a browser-based interface. The operator begins by selecting the job type. Two paths are available: training and inference. We focus here on the inference path, which is where continuous production AI serving takes place and where the energy waste problem is most persistent. We select code generation, representing an AI coding assistant workload involving small code checks and corrections. The system now asks the operator to define the latency budget, an SLO. This is the primary control lever in the entire workflow. At a 2-second constraint, only the smallest model, Mistral 7B, is eligible. Increasing the latency budget unlocks additional models. Mistral 7B is marked as the most energy-efficient option, while Qwen 2.5. Coder 32B is flagged as best performance. The system shows energy performance trade-off directly here, before any job is submitted, so operators can see quantified differences across model options at their chosen SLO without needing GPU expertise. We select Mistral Small 24B, a balanced choice. The review page summarizes the complete configuration, and the system has generated the full job script, which can be submitted via Slurm, a high-performance workload manager and job scheduler, automatically. Scrolling down, the operator clicks Submit Job. The system confirms successful deployment on the cluster. An automatic redirect takes the operator to the inference dashboard, which opens connected to the running job. The Halo Inference dashboard opens on its first tab, Modes and Savings. Two configurations are shown side by side. On the left, the baseline is shown, representing the reference showing the GPU running at maximum frequency throughout, which is common practice, with no adaptive control. This is the default production state, predictable and high-performing, but energetically unoptimized. The baseline establishes our comparison point. Everything Halo achieves is measured against this. Moving the SLO slider on the Halo card to 10 seconds reveals the maximum savings achievable under Halo. With greater latency slack, the controller can operate at substantially lower GPU frequencies more aggressively and for longer periods. This is the core result. Halo delivers close to 40% energy savings while fully maintaining throughput. It fulfills the defined service level objectives and realizes the AI inference cheaper without losing service quality. Switching to the Live Monitor tab, we observe the real-time replay of the inference run with real-time GPU SM frequency and energy consumption. This is Halo adapting in real time, not following a fixed rule, but learning the energy latency trade-off landscape online and converging to the best frequency for the current conditions. Where prior analytic systems provided visibility over energy and cost trade-offs, this system provides actionable decision support, a runtime controller that adapts GPU frequency under live service constraints, guided by a decision support layer that covers configuration, monitoring, and outcome reporting. The savings are validated on a real inference trace at production scale, with close to 40% in energy. Imagining a large-scale data center, a conservative scenario of 7 seconds SLO still achieves 27% energy savings with Halo, which would lead to yearly energy cost savings of around €57,000 and reduced CO2 emissions without compromising service quality.